Good morning. So I'm supposed to talk to you today about nuclear quantum Monte Carlo calculations. This is work that's been done with many colleagues, particularly over the years Steve Piper, Joe Carlson, and Rocco Scavilla. And we have a lot of computer support from various things at Argonne, including the newest Blue Gene Q, the Mira, which you heard some talk from Alessandro Lobato on Friday, discussing some of the calculations and with that. Oops. So we are interested in doing ab initio calculations of light nuclei. By that I mean calculations starting with bare nucleon-nucleon forces that have been fit to nucleon-nucleon scattering data. The types of things we want to evaluate are binding energies of nuclei, excitation spectra, densities, electromagnetic moments, transition amplitudes. We also want to do nucleon-nucleus and nucleus-nucleus scattering and things important for astrophysics like asymptotic normalization coefficients. The requirements are, first, a good two-nucleon potential that accurately describes elastic nucleon-nucleon scattering data, and then consistent three-nucleon interactions and electroweak current operators. And, of course, an accurate method for solving the many-nucleon Schrodinger equation, which is what the nuclear quantum Monte Carlo gives us. The chief results I hope to show you are that we can evaluate realistic Hamiltonians accurate at 1 to 2% in the binding energy. For electronic structure, that would be terrible, but for nuclear physics, that's pretty good, especially since we don't really know what the force is. We've done about 100 states up to A = 12, and generally good agreement with experiment. We've many applications to various reaction problems, electron-pion scattering, DP reactions, things like that. Calculate electromagnetic moments and transitions, M1s, E2s, Fermi, Gamow-Tellers. And we've also done one nucleon-nucleus scattering case for helium-5, and we've done some approximate calculations that give us asymptotic normalization coefficients and widths up to A = 9. So the nuclear Hamiltonian. We don't really know what the nucleon-nucleon force is, and maybe someday lattice QCD or some form of QCD will tell us in detail. But for the moment, we're going to be doing non-relativistic quantum mechanics, one-body kinetic energy operator, two-body potential, and three-body potentials. The kinetic energy is standard, non-relativistic, but there is a small term for the proton-neutron mass difference, which we keep track of. The two-body potential we use is argon V18. It's our own construction because it has the properties we need. It's both a good fit to nucleon-nucleon scattering data, but it also has nice properties for the many-body techniques that we use. It's composed of one long-range, one photon exchange, a complete, not just Coulomb, but magnetic moment interactions and other terms. One pion exchange, which has a spin-spin and tensor times isospin structure. Intermediate and short-range parts are phenomenological. The intermediate part is given the range of 2 pion exchange, and the short-range part is just a Wood-Saxon phenomenological structure. Parameters to be fit to data. The operator structure can be written this way. There are 14 charge-independent terms. The first 8 terms here, central, spin, tensor, and spin orbit, and any of those times isospin, are the most important ones. They're the ones that allow you to fit S and P wave nucleon-nucleon data. To fit higher partial waves, you need some sort of velocity dependence, and by using L squared as that source of velocity dependence, it leaves the S wave potential static and effectively the P wave potential static. And that's helpful again because they're the most important parts of the interaction and makes the many-body calculation easier. In addition, there are some small charge-dependent terms that have this isotensor operator. Some of these are coming from pion exchange, just the fact that neutral and charged pions have different masses. Proton-proton scattering, you can only exchange a pi naught, but neutron-proton scattering, you can also exchange charged pions, and that gives some small terms here. And then there's also a piece of charge symmetry breaking that we put in to fit the one piece of neutron-neutron data we have, which is the scattering length. These 3 green terms only come from the electromagnetic part. The 18 strong terms is why it's called V18. Some logic. When people do nucleon-nucleon scattering, both proton-proton and neutron-proton, they collect, at the time this potential was made, over 4,000 pieces of data, cross-sections, differential cross-sections, polarizations, asymmetries of various kind. Those are commonly processed into an intermediate step, in a partial wave analysis, to phase shifts. And these are some of the the first low orbital angular momentum phase shifts, singlet S, triplet S, and so on. And we fit up to about 350 MeV in the data. And these are compared here to a more recent phase shift analysis for data in this case, up to 600 MeV, just to show that not only did we get originally a very good chi-square up to 350 MeV, but qualitatively we're good to very much higher energies. And these are just what some of the shapes of the potentials look like, different terms, central, isospin, spin, and so on. The central term goes up to about 2 GeV, which some people consider difficult to handle. For us, it's not a problem in the many-body calculations. There are some 40-odd parameters in the intermediate and short range that have been fit, basically one intermediate and one or two short-range parameters for 18 different operators. And they're constrained so that the tensor potentials go to 0 at the origin, and the other potentials are flat at the origin.
Well, assuming in the previous slide, you showed the phase shifts up to, you calculate up to 600 MeV. I suspect you solved the Schrödinger equation, not the Dirac equation, something like that, correct?
That's correct.
It's a very high energy, 600 MeV. Its Fourier relativistic effects are very strong there. So what's the meaning of comparing phase shifts if you claim?
Well, the two-body problem, you keep track of both, K and E lab are the same whether you're doing it relativistic or non-relativistic, if you work out the expression. So that it's the proper relativistic kinematics is in there. Certainly at 300 MeV you start to have pion production inelasticities, but the inelasticities stay very small in most channels for a much longer range.
What about the dispersion? It's not K-squared anymore. K-squared was there.
Let's talk about that afterwards. I think we're fine.
I think it's fine. If you look,
I'm simply asking.
Yeah.
I simply want to know if you
what he said, I think is correct. Relativistically, as far as the kinematics go, it is you get del squared plus k squared, and k squared is calculated relativistically from E lab.
Yeah.
And that works out to be the same equation as it does non-relativistically. But it may assume two equal nucleon masses.
No, we actually, even in NP, we have the relativistic correction for NP.
Okay.
So, as you'll see in a few minutes, two-body potentials give us the bulk of the interaction, but they're not enough. As soon as you go to the three-body system, you already find you're missing some of the binding. So, phenomenologically, we have to add three-body potentials. From a practical point of view, or fundamental point of view, you certainly know that the nucleon is a composite object with an excited state spectrum of its own, and you would like to start taking that into account. In the two-body system, it's there implicitly in the potentials in a sense. But once you get to the three-body system, you have diagrams like this where pion exchange excite a non-nucleon state like the delta resonance and then de-excite to a third nucleon. And this is the famous Fujita Miyazawa three-body force. It's more than 50 years old. So we built our first series of potentials, basically this plus a shorter range phenomenological piece for repulsion, which we found we needed. And you can think of as coming from a plethora of different possible diagrams that could contribute. And then we took two parameters and fit them basically to triton binding energy and a nuclear matter calculation for the saturation density. There were a series of these potentials as different things changed over the years. In about 2000, we started building Illinois series, which we supplemented the P-wave pi nucleon scattering off an intermediate nucleon with an S-wave, which the chiral effective field theory people said was important. Actually, in this term, it's actually about an order of magnitude smaller than that in practice. And we looked at other possible terms. We found phenomenologically we needed some additional isospin dependence that we were not getting from these terms, and eventually we found it by looking at these 3 pion ring terms. So basically, in the Illinois forces, we have a coefficient for that, a coefficient for that, one for these, one other coefficient floating around. This we take from chiral effective field theory, basically the strength. So the Illinois 7, which is the current, most recent, our best model, has 4 strength parameters, fit to 23 energy levels up to A equal 10. Two-body forces fit to two-body data. It's not being altered. So in light nuclei, of course, you have a big cancellation between one-body kinetic and two-body potential. And although the three-body potential is usually a small fraction of the two-body potential, it can, in some cases, be a very large fraction of the binding energy. In principle, there should be 4-body and higher forces because you've suppressed non-nucleonic degrees of freedom. If you think you have an average convergence, something like this, and there are, again, arguments from chiral perturbation theory why you should get fairly rapid convergence, then you might expect the missing terms to be a few percent of the expectation value of the Hamiltonian, on the order of an MeV in carbon, perhaps. And the fact that you're fitting the 3-body force to a lot of data, maybe you are mocking up some aspects of 4-body forces and higher. You're probably also mocking up some features of relativity, of kinematic relativity. So our calculational method. We do 2 steps. We do variational Monte Carlo first. We minimize the expectation value of a trial function to get an upper bound to either the ground state or the lowest state of given quantum numbers. We do the integration by metropolis. The type of wave function, we have fairly sophisticated trial functions. You start off with a single particle wave function. It's fully anisymmetric and translationally invariant by having basically whenever you have a function of R for a particle, for example, in the P shell, in fact, we write it relative to the center of mass of the S shell, whatever the configuration is. So that keeps all the coordinates relative and therefore translationally invariant.
You said the center mass of a given shell?
Of the S shell. So when you build...
The whole nuclei. Why not the whole nuclei?
You could in principle do that, but we find it's not terribly different. You just have to have somewhat different radial functions to get... We're going to vary the shapes of these to minimize energies. It's just the most convenient thing we could do, and it does guarantee translational invariance. So you construct a single particle wave function with a total J and J projection, isospin, charge of the state you're interested in. You act on it with a product over all pairs of a central correlation just to keep, since there's a strong repulsive force at short range, to keep them from sitting on top of each other. There's some confinement provided in single particle functions here, and these also provide some confinement. So the pair function falls off as you pull particles away from each other. And so the general confinement into a nucleus is provided in these shapes. Then on top of that, you act with a symmetrized product over 2- and 3-body correlation operators. So the UIJ are 2-body operators. They're also a sum of operators. They have spin, tensor, central, isospin terms. And they're designed to reflect the influence of the 2-body potential, which has for example, strong tensor forces. And when there's a 3-body force present, then you also have a triples correlation, again with spin and tensor dependence in it to reflect the 3-body potential. We construct states of multiple, as you get up into the P shell, and it's 5, 6, 7-body systems, there are multiple ways of adding up the orbital angular momentum and the spin to get the total J, and we construct all the same states that you would have in shell model, and then we diagonalize in that small basis to get the lowest state and multiple excited states. One of the freedoms of this is we are not in a basis, we're not in a harmonic oscillator basis or any other basis, we're just in space, and it gives us a lot of freedom to construct wave functions that are clusterized, or in some cases you can make sure that the asymptotic tails are correct, although that's not always necessary to get a good energy. The problem is that these wave functions are spin isospin vectors in 3A dimensions. In practice, we keep all 3A dimensions, but they are translationally invariant. And the spin, because again, of the tensor force, spin is not conserved. So although, for example, the alpha particle, think of starting out as spin up proton, spin up neutron, spin down neutron. The full wave function has about 15% D state. It means there's a significant component of all spin up and compensated by having orbital pieces induced by the correlations of L equal 2, so that the total J is still 0.
Isn't there any good, I mean, you say that you have triplet correlations only in the presence of the three-body force.
Well, there are some additional small central three-body correlations that we use, but they're not terribly important.
Okay. No.
There are some others scattered through here, but there are important when you have a three-body force, which we almost always have, and they have the same tensor spin structure as the force. So at any rate, the psi v are spin isospin vectors with 2 to the A possible spin components. You conserve charge, but in principle you could have binomial A over Z isospin components, or charge components. In practice, in fact, we find that you can conserve isospin is a good quantum number most of the time in nuclear physics, so you can reduce that A over Z sum. This is an idea of how a calculation scales with the size of number of particles. Basically, it goes as the number of particles, because as you construct the way, we do the kinetic energy by brute force. You sit there and move each particle plus minus x, plus minus y, plus minus z, reevaluate the wave function every time and take finite differences. The wave functions correlations of the wave functions are complicated enough, you just can't consider using chain rule on some, they're not Gaussians or something. So you really have to do it. So the kinetic energy calculation goes to the number of particles. Constructing the wave function goes to the number of pairs because of all those pair operators. And Alessandro Lovato on Friday showed you an example of how a sigma dot sigma acting on the spin isospin vector would rearrange, alter and rearrange certain terms, and you do that successively over all pairs. The size of the spin isospin vector, this is taking into account the isospin conservation, so it's not the full binomial A over Z. And in some cases, you can save on the spin a factor of 2 if you're in an m equals 0 state. But basically, this is how things go up. If you think beryllium-8 as a standard for now a fairly simple calculation, carbon is about 500 times more complicated. And that's the limit of where we've been calculating at present. Again, Alessandro's calculations to do some electromagnetic sum rules in carbon are probably an order of magnitude more expensive than just doing energy calculation. So we're getting close to being able to do maybe 13 to 14 body systems. But obviously, much larger systems are just out of question for the moment.
Why don't you have triplets? Why is your scaling not 8?
Okay, so the number of triples also goes up, but since the three-body force is a lot smaller, you can actually get away with sampling them rather than calculating all of them. But for the two-body force, we feel we have to evaluate the full spin isospin vector. We never figured out a way to...
You have this Uij. Why isn't that triple in there?
The triplets of the wave function.
You have this product of the Uij.
Well, this one, though, you can sum over the third particle and build this into an effective two-body correlation. So that that saves time.
How do you optimize all your parameters?
Without saying in detail, there are order 40 or 50 parameters in here, and it's 20 years of man effort working on. Actually, once you have the alpha particle pretty good, and the alpha particle comes out pretty good, most of the effort is not in, you find that these correlations tend to stay pretty much the same, and it's getting the single particle structure optimized. That's really where most of the effort goes. And part of that is building all the possible states and then doing the diagonalization within those states too.
So there's no commutator terms in the Uijk, is that correct?
That's correct. We only do the anti-commutator part of the three-body force. Then this next step is Green's function Monte Carlo. I should say I'm the variational expert. Steve Piper is your Green's function expert for actually doing the work. Of course, this depends a lot upon the background of Joe Carlson, who developed the technique, or applied it for nuclear physics, developed it from his experience with Mal and coworkers to apply it to nuclear physics. You project out the lowest, well, you guys all know this, you project out the lowest energy from a variational trial function. You're going to the lowest state of given quantum numbers. The evaluation is done stochastically in small time steps. You have a small time, very good small time approximation for the Green's function. It's built out of a product of exact two-body Green's functions normalized by just the kinetic terms. For doing operators in general, we use mixed estimates. So you would like, of course, to take, this gives you samples of the wave function at propagated time tau. You would like to take those samples and do an expectation value of an operator at time tau like that, but we approximate it by the mixed estimate, where you have tau on one side but the original trial function on the other side. In the particular case of the Hamiltonian, you have, of course, this feature that you can commute half of the operator there across. So in principle, your Hamiltonian is in fact an upper bound, but for other operators, you have this mixed estimate. The drawbacks, we don't have a way to propagate p squared or L squared type terms in the Hamiltonian. You could do a single one, but there's no single one that would improve your representation of the two-body force. You would have to have p squared or L squared times spin and isospin, and that would make things difficult. So in fact, we use an H prime, which is what we call the AV8 prime. It's basically a reprojection of the V18 into the first 8 operators. So basically it reproduces the S and P wave parts of the potential, and the remaining terms of the potential will be calculated in perturbation. But one of the features of the V18 is that in fact those remaining terms are relatively small perturbation. The bulk of the potential is here. And we also use a variation on the three-body potential. It's basically most of the structure of the three-body potential, but we artificially, this tends to be a little bit too attractive, so we jack up the repulsion here so that the expectation value of H prime will be about the same as the expectation value of the full potential once done in perturbation. That way you won't artificially bind something too tightly for an overbound potential. We have a fermion sign problem, but it's, we use constrained path propagation with relaxation or a removal of the constraint afterwards, very much like Shiwei talked about yesterday. The main difference here is, again, that we're working with these wave functions. They're this big vector and spin isospin space, so it's the dot product that you look at. There's no node in individual, there's no place you have a node through all the components of the wave function at the same time. But you make sure that the steps you throw away are the things that are on average 0 content.
Could you say a little more about that? I'm not an expert.
So you didn't see Shiwei's talk yesterday.
No, I
Shiwei, would you like to say a little more? It's basically, the idea is you have a constraint which is provided by your trial wave function. You want to throw away terms when the dot product of these things changes sign to remove the noise. You don't want to go to a boson state. In practice, sure, say anything you want.
No, that was my voice. If
I'm sorry.
psi v in that expression were the exact, then this constraint would be exact.
Yes.
Okay.
Can we talk about it in more detail afterwards? And then one of the things that's sort of surprising is that, or we were surprised when we actually did it, but if you start out with trial wave functions that are orthogonal, then in fact the GFMC often keeps them orthogonal. So you can in fact propagate states of the same J pi that are higher in excitation. And I'll show an example of that in a moment.
Because of the constraint.
Partly the constraint, but
But
yeah.
sometimes,
So these are some standard examples of
It's also a validation that your Green's functions are accurate.
that the Green's functions are accurate and that the trial wave functions are good.
Yes.
That's my part. So some examples of the GFMC propagation. Here is a fairly old result for 4 helium up to very small tau. It starts off with at tau equals 0 is the trial function. In fact, we can do much better than that nowadays. It drops fairly rapidly, goes to a constant. If you try to fit this with an exponential curve, again, assuming that what you're doing is knocking out higher excited states, you put in the known first excited state for helium-4, which is 20 MeV for the 0 plus excitation, and fit 2 more, and you find basically that, in a sense, what's wrong with the trial function is some very small contamination of very high excitation. And the GFMC is excellent at getting rid of that very quickly. In the P shell, it's not quite, you still have this very rapid drop. Now I'm showing an example of propagation out to very large tau for the ground state and the first 2 excited states. 6-lithium is not stable, is barely stable. It's 1.5 MeV bound against separated alpha plus deuteron. The trial function that we start with, in fact, is not stable against that breakup. But these dots are energy evaluations, and there's something like 20 or 40 little small time steps in between before you do an energy evaluation. Already within the first 20 or 40 steps, one is at an energy that is stable against breakup, and the energy very rapidly saturates and you can get a very nice energy out of it. The 3+ state is actually not stable against breakup, but it's a very narrow state physically, and so in fact the energy comes down and is very flat, and you can read off the energy. The 2+ state is in fact physically a very wide state, and you see again an initial rapid drop and then just a constant drift. So presumably that is going off to alpha plus deuteron in a relative L=2 state, or L=1 state actually. So you really should treat that as a scattering problem. But for the beginning, to just estimate the energy, you can extrapolate back and say, well, this is, at this tau, we already had most of the energy improvement from GFMC. We'll just read off the energy there and use that.
Do you see it becoming alpha plus deuteron?
You certainly see it getting much bigger. I don't think we've ever tried to actually
Deuteron's pretty big.
project out. The deuteron is pretty big, and I'll show an example later of a similar problem. Here's an example of doing them for states of the same spin and parity. So this is 7-lithium, 5 halves minus state, has 4 different spatial symmetries within the P shell. The trial wave function has been diagonalized in that basis, and these are the energies as a function of tau for the first, second, third, and fourth states. And in fact, again, this is a case where the first state is actually moderately wide. It's disintegrating to an alpha plus triton in an F wave. And there's a slight slope there you don't see, but here's the other energies are pretty stable. The top one is also decreasing. It's a very wide state. It's not surprising it's going to fall apart. But these energies are very flat overall. So again, you can pull off energies. They've stayed orthogonal. If you look at the overlap of psi2 with psi1 during the propagation, it's pretty flat. Some of them are a little bit bigger. If you feel you want to, and we checked, in fact, in this figure, there are both open and closed circles. I believe the open circles were straight with no alteration, just propagation. The closed circles are the ones where you have explicitly reorthogonalized at each step. You can do that, but you can see for the energies, it's not making much difference here. So this is the sort of standard figure. There's no date on this one. I prefer to show it without a date, and I actually have a more modern one at the very end of the talk that adds a couple more states in carbon-12. This is basically, again, summary. Two-body forces fit the two-body data not altered. The three-body forces parameters fit to 23 states. For some 51 states here, there's an RMS 600 kilovolt RMS error. And there's also about 60 isobaric analogs, which we're not showing in this figure. The left-hand side, that's for the 2 plus 3-body force. The left-hand side, the blue figure lines are just the 2-body force alone. And you can see that already at the alpha particle, you're missing about 4 MeV of binding. And by the time you're up to carbon, you're missing about 20 MeV of binding. But you should remember, this is a spot which has about 500 MeV attraction from the 2-body potential and about 430 MeV one-body kinetic energy. So that huge cancellation is why the 3-body force really stands out in the binding energy. But 20 MeV for the 3-body force versus 500 MeV for the 2-body force, the 3-body force is sort of perturbative. Mm-hmm.
You said in practice you use the AV8 prime and then go to the full with imperturbation theory, and
Yeah.
that's why you put the full on
Yeah.
the title.
Yeah. This is just a picture showing them a lot of that same data as excitations where all the ground states have been lined up. And again, you see another important feature of what the 3-body force does for you. The 2-body force already in some places, the excitation spectrum is not so bad. But you see, for example, here in lithium-6, this is a triplet of states which are spin orbit split. And basically the 3-body force increases that splitting much closer to the experiment. So the 3-body force is introducing a certain amount of effective 1-body spin orbit splitting. And there are other places where this becomes important. For example, in 10 beryllium, there are 2+ states experimentally. With the 2-body force only, they're basically degenerate. With the 3-body force added, they split quite a bit. They're not quite up to the split of the experiment, but they're much closer. And the most dramatic case is 10 boron. The ground state is a 3+ state, but if you use only 2-body forces, you get a 1+ ground state instead. And this has been confirmed by other people using different 2-body interactions and 3-body interactions and different calculational methods. If you don't have if you have only 2-body force or you don't have a decent 3-body force added to it, you'll get a 1+ ground state for boron, and it's not correct.
The fact that even when you have 2-body forces, sometimes you get, I mean, these are excited states, so I guess that, but you're not variational in any case here, right? I mean, the fact that you go below the experimental values with even with 3-body forces, for example, variability.
Yeah.
Is that the Hamiltonian, or is that the fact that you're not variational?
We think at this point we're testing the Hamiltonian. And again, we don't really know, there is no unique nucleon-nucleon Hamiltonian.
Exactly. No, I understand.
So at this point, we...
States, I mean, in principle, you're not variational any longer.
Well, you mean because of the GFMC, the constraint? Well, again, we do what Shiwei did at the end of his talk. We follow a constraint, but then at the end we always release the constraint and take another 20 to 40 steps and see if the energy shifts. And we study how many steps we have to do that. So that's something we allow for. So I thought Alessandro would show a little bit more about carbon-12 on Friday than he did, but I thought I'd better show what the ground state calculations are. So this is to try and do the first and second 0+ states in carbon. The Hoyle state is this famous astrophysically important state that is the key to triple alpha burning. So to construct it, again, in the P shell, there are basically 5 different symmetries that you can construct that add up to 0+. And Joe Carlson gave us a simple way of doing that by filling basically a P3 shell and then doing projection operators on it. The dominant feature is going to be, though, a triple alpha symmetry, 3, which is basically a big overlap with this. And what we can do with our freedom to construct the wave functions, so we're not in a basis, is you put 1 in the S shell and 2 in the P shell, or you take one of the P shell ones and you can promote it to the SD shell, or you can break it apart when you promote it. And so you end up with a number of additional components that are allowed different ways of breaking up or moving that last alpha around, basically. In the end, there's something like 11 components that, again, you do a diagonalization in. And here it is a more challenging job. You have to do a rediagonalization step by step as you do the propagation to keep that second state orthogonal. The first state goes very well. And so here's the propagation for two different trial functions, two different starting trial functions for the ground state and two different starting wave functions for the Hoyle state, and the triple alpha resonance is right there. So the energies are very stable. If you do two-body force only, you have this 20 MeV underbinding. You pick up about 30 MeV from going from VMC to GFMC, and then you pick up 20 MeV by adding the three-body force, and you're very close to the experimental value. For the second state, we end up with, these are the excitation energies relative to the excited state. Experimentally at 7.6, we end up a little bit too high. And that's probably saying the Hamiltonian is not good enough. We think these calculations are accurate enough for that Hamiltonian. If you look at the charge radius, the ground state is perfectly stable in both calculations, and that is the experimental charge rate. These are the point proton radii, but you convert it to charge radius, and it is the experimental value. On the other hand, for the Hoyle state, it's very hard to tell what the radius is, except it's bigger. And these are what the density profiles look like. For the ground, now the blues are the ground state open symbols of the starting variational wave function, which is a little too peaked in the center. The GFMC corrects that and brings it down. The black is the experimental charge density is inferred from electron scattering data. So that works out very beautifully. And then the red is what the Hoyle state is doing. And again, the variational wave function is being moved around a fair amount by the GFMC, and in fact is building up a peak in the center. So maybe that means that whereas the ground state is probably more or less 3 alphas in a triangle, and therefore there's a dip in the center in the density, probably that central in the Hoyle state, one of those alphas is getting more toward the center and producing a peak. Well, I've already used up a lot of my time.
Well, the Hoyle state a bit. So if I'll take 3 alphas from your calculations, the energy of 3 alphas to be below the Hoyle state would be obtained, correct?
Yes.
So basically what your calculations show that you have a repulsion within the 3 alphas in that.
More than necessary. Yes.
So that's a bit surprising, because if you look at Beryllium-8, you basically obtain that slight widening there, right?
And beryllium-8, it's just unbound, and we get just unbound. But you're testing the Hamiltonian, and maybe this is,
But this
no.
will be the long-range part of the Hamiltonian, and you're getting kind of...
No, not necessarily. No, I don't think it's the long-range part.
Well, the alpha particles, you see, don't barely touch each other, right, in the Hoyle state.
You're here on a very slippery slope of, the three-body forces between, crossing between the two and even 3 alphas, and it's a complicated calculation.
So you don't know why you're paying too much repulsion.
I think the Hamiltonian isn't quite right,
Well,
but
you don't know why it's not right, right?
I can't say, I can't point to any term and say, oh, that's obviously wrong. No. So I was going to show lots of other sorts of physics results. One of the, okay, I'll go as far as I can. Nolan-Schiffer anomaly. Again, I mentioned at the beginning that the charge-independent forces, the one that have 1 or tau dot tau as coefficients to the spin tensor, spin orbit stuff, are by far the dominant, but there are these small charge-dependent and charge symmetry breaking terms in the Hamiltonian, and electromagnetic forces mix all that up too. You can find evidence for charge independence breaking from, one way is to look at isobaric multiplets. For example, to look at the binding energies of 3 helium and tritium, and you figure most of the central forces in a sense will cancel out against each other. So when you look at the difference, this selects out the charge symmetry breaking pieces. If you write the energy as a function of, sort of an expansion in 1 or the charge or sort of a charge tensor, isoscalar, isovector, isotensor components. These are what the calculations, by far the biggest component, for example, in the triton three-body energy difference calculation is the Coulomb force. But experimentally, it's more than 100 kilovolts larger. And you find that, in fact, you pick a lot of it up from the charge symmetry breaking. This is the fact that the neutron-neutron force is slightly different than the proton-proton. Unfortunately, the only piece of neutron-neutron scattering data you have is the scattering length. And the potential was made to fit that difference. And you also pick up pieces from the kinetic energy difference because of the proton-neutron mass difference and other terms in the electromagnetic, like magnetic moment interactions. And you end up coming pretty close. And another case is the A equals 7 lithium, 7 beryllium. You don't do quite as well on charge-dependent cases when you look at isotensor combinations like 6 beryllium, 6 helium, and the isobark analog excited state 6 lithium. You're trying to find something that's about an order of magnitude smaller. And this one's embarrassingly large, but this one's not too bad. At any rate. Another place you can look is isospin mixing in beryllium-8. And I was going to talk about beryllium-8 on several occasions if I could get far enough. Beryllium-8 has a really interesting spectrum. It is just unbound against breakup into 2 alphas, but it's an extremely narrow resonance, 6 electron volts, not kilo electron volts, it's electron volts difference. And then it has a rotational spectrum. It has basically a 2 plus and a 4 plus state that are physically very broad. And then when you get up here, you start seeing a second 2 plus, T equals 0, and an isobaric analog of 8 lithium, 8 boron. So in fact, there are 2 2 plus states here that are right on top of each other, one T equals 0 and T equals 1. And the charge symmetry breaking parts of the force can mix those. And there are similar triplets of 1 plus and 3 plus. And this is a classic two-state mixing problem. Experimentally, you see these decay by alpha decay into 2 alphas. And you can only, since those are T equals 0 system, it's only the T equals 0 component that can do that decay. And so it's very simple to take the widths, experimental widths, and figure out the mixing. So if I write the wave functions as a linear combination of T equals 0 and T equals 1 states, the 2 eigenvectors, and you can figure out what the mixing is, and you can figure out what the actual energies of the states are, experimental energies, and work backwards to figure out what are the unmixed energies. And you find that the original unmixed states are only about 60 kilovolts apart. And there's a mixing matrix element that's like 140 kilovolts. So we have calculated that in again, taking expectation value of the Hamiltonian. This is an off-diagonal matrix element because you have a T equals 0 and T equals 1 states on different sides. And so in that case, we have to do a mixed estimate again. You would like to evaluate this quantity in JFMC, but we can only use trial wave function on one side. We tried looking in the literature for what's the formula we should use. Well, in a sense, it's kind of obvious, but we didn't see it written up anywhere, and maybe somebody in the electronic structure community can tell me an example where that's written down. But basically, you want to do one mixed matrix element where the initial state has been propagated, and what the output of the GFMC is this psi I of tau weighted by psi I of the trial wave function. And you want to dot it against the psi trial of the final state, so you need a correction factor, normalization from the ratio of the trial functions. And then the second mixed estimate should be the one where the final state has been propagated. And these are the GFMC results for this particular problem of the isospin mixing. Again, the thing is that the Coulomb part is only about half of the empirical value, and the other terms that are the full electromagnetic interaction and again the explicit charge symmetry breaking the force add up to make a larger fraction, although they don't quite match the experimental value. This is something we're actually redoing these numbers right now and writing it up for publication. We do single nucleon densities. Easy thing to do once you have your wave functions. A good example here is for the helium isotopes, 4 helium, 6 helium, 8 helium. This is something we're particularly proud of. The charge radius for helium-4 has been measured very precisely in electron scattering experiments. But until about 10 years ago, there there's no good way to measure these charge radii because 6-helium only lives about a second before it beta decays, and 8-helium about 1/10 of a second. However, there's in the 1990s, somebody had done an experiment to measure the charge radius of 3-helium by trapping 3-helium, which is stable, and looking at the changes in the atomic excitation spectrum, the fine structure that can be attributed to changes in the charge radius of the nucleus. So this depends upon having very good electronic structure theory, and which you can do at the 1-2 electron level, and then these very precise trapping experiments. We suggested this as a problem to our colleagues. We had calculated our charge radii. We suggested as a problem to our experimental colleagues who were doing neutral atom trapping. Can you trap 6-helium and 8-helium? Well, a real tour de force in the experiment. They went and they produced 6-helium in the accelerator in the back of our building, the Atlas accelerator, moved it into a trap, bombarded it with lasers, measure the radii, and measure the changes in the atomic spectra. To initially tune their lasers as to where they were going to go, they said, well, we'll take your estimate as the best first guess, and they saw the signal in the first hour. So this is a case, the energies that we're trying to calculate have been known for decades, many of them. So we're all post-dicting those things. But this was a case we could actually predict something in advance, and it turned out to be right. So one of the features here you see in 4-helium, of course, is a very compact nucleus. It actually has a very high density peak, although there are very few nucleons when you weight with R squared in that region. Once you add an extra 2 neutrons outside, you start spreading things out a bit. So a lot of the time, the 2 neutrons in 6-helium, extra 2 neutrons are way out to one side, so the center of mass is shifted, and that's why the charge radius changes significantly. We also do 2 nucleon densities. They're easy to, again, calculate. And for the same nuclei, it's an interesting question. If you look at the proton-proton 2-body density in the alpha particle, you have these magenta curves. You think, okay, if I put 2 neutrons outside that, how much does it tug the alpha particle apart? And you see it does change it a little bit. It lowers the peak here a little bit, and it's compensated out here because the integral under this curve has to be 1 for each of these cases, since there are 2 protons in each case. Another thing that's sort of fun to do is to try and, again, the question of where are the nucleons in a nucleus. And this was an idea that Steve came up with. We've only done it with the trial wave functions. It might be possible to do it with the GFMC, but we haven't tried to do that yet. As you do a walk, the Monte Carlo walk, with the trial wave function for 8 beryllium, at every time you have an independent, you do a number of attempted steps, and then you have a configuration at which you're going to evaluate the energy. You have the positions of all the particles in space. You can compute the moment of inertia tensor and then diagonalize it. There's some particular, and then rotate the particle that's furthest away from the center of mass, rotate it to the z-axis, and bin it. And that's what's been done here for the ground state, for the 0 plus ground state. If you don't do this rotation, you just get a 0 plus distribution. This is the z coordinate, and this is the r, the cylindrical coordinate. If you do this rotation every time on every configuration, you're going to build in some sort of deformation. That's inevitable because you're always putting the farthest one along the z-axis. But when you do that here, you actually see a very definitive 2-bump structure. And so this is really the intrinsic structure of the 2 alphas. In the 0 plus case, it's just rotated randomly, so you don't see anything in the lab. Here's the 4 plus case, done the same way, and again you see basically the same intrinsic structure, and now in the lab you start to see the actual rotation comes out.
That has the same eigenvectors as the moment of inertia matrix, but that's not the moment of inertia matrix.
Sorry. Here's another attempt to try and understand the structure of, get some visualization of where nucleons are in nuclei. And this is doing a 2-nucleon halo densities for a system, again, like 6-helium. How do you identify the last 2 neutrons out there? And sort of a trick I came across was to use double isospin raising operator, sort of like would be used in double beta decay, acting on the TZ equal -1 state and dotted against a wave function that's the TZ plus 1 state on the other side, but otherwise identical. It's just interchanging protons and neutrons. And basically these raising operators, anything that's in the alpha core, you can't raise a proton in the alpha core without getting 0. So it kills the alpha core off, and basically you get 1 neutron-neutron pair, and then you can try to bin it, not just as a function of the neutron-neutron separation, but also the separation of the center mass of that pair from the core. And you get this sort of a double bump structure in the ground state. The big bump is where the neutron-neutron separation is not so big, so these are 2 neutrons off on one side, away from the core. But there's a second bump where they're on opposite sides of the core. And you can do the same trick for the excited state, the first excited state, 6-helium, and you don't see any structure. Basically, things have spread out. You do the same thing in 10 beryllium, which is very much a beryllium-8 core, 2 alphas, and then 2 more neutrons. And the ground state has a very similar structure to the ground state in 6-helium in the layout of where the last 2 neutrons are, mostly off to one side. If you look at the first 2+ state, it actually stays the same. It's not like this state, it's like this. And basically, this is probably because the first 2 pluses, the beryllium-8 core is what's rotating and giving the J equal 2. And the 2 neutrons are still in basically a relative S wave. And then you can look at what happens in second 2+ is more like this. The second 0+ is actually sort of anti-correlated with this. Now the 2 neutrons are probably on opposite sides. David was talking about doing momentum distributions in systems. We also try to do momentum distributions. Again, this has so far only been done for variational wave functions. We're talking about how to do it in GFMC. It's a little bit, the trick that we use to actually carry it out with good statistics requires acting on moving particles on both sides. And we wouldn't have that freedom of moving a particle on the GFMC because we only have samples on the GFMC side. So we're still thinking about how to do that. But if you want to see, you can go click on that link and see lots and lots of momentum distributions. Another thing we tried to do are transitions. The last several years, again, these are going to be off-diagonal matrix elements of operators like for an E2 transition, electric quadrupole transition, it's basically just an R² times a Y2. For a M1 magnetic moment transition, it's basically the magnetic moment operator, but wedged between different states. And you can also look for Fermi and Gamow-Teller transitions. These were calculations we did. The blue dots, okay, so this is ratio to experiment. The black stars are the experiment, and sometimes they have error bars if the experiment has error bars on them. The blue dots are a straight GFMC calculation with these one-body operators for a variety of 6- and 7-body systems, and generally pretty good agreement. There are 3 M1 transitions here where they're all low, but they then went back and added explicit 2-body current operators, which again you expect on the basis that nucleons are not fundamental particles, and you can have pions being exchanged with them, so there are 2-body currents going on in the system. And adding those operators back in and their contribution to the M1, in fact, these all end up right on the data. And these are magnetic moment calculations. These are done with a newer version of the exchange currents based on chiral effective field theory. Again, the black stars are experiment, the blue are impulse approximation, GFMC, and the red are the full with 2-body exchange currents added. The 2-body exchange currents have a few parameters that have basically been fit in the 2- and 3-body systems, and then all the rest is prediction. And again, the predictions are very good. In some cases, impulse is already very close to experiment, so you don't want a big exchange current and contribution. In fact, it is small. In other cases, you need a big exchange current to get close to experiment, and it works out okay. And then we've done push the some of the transition calculations to larger A equal 8 and 9 nuclei. And these are some details about what goes into those chiral effective currents, but I won't dwell on that. Let me go back to beryllium-8 again. We're also working now on transitions there. We didn't do these at first because beryllium-8 itself doesn't have a magnetic moment. We are focusing on the magnetic moments and doing the transitions in the same systems. So we want to do these E2 transitions and the M1 transitions between these isospin mixed states, and eventually also, again, these weak decays. But those are more difficult to do because they're not what are called super allowed states. At any rate, the GFMC does a pretty good job of reproducing the spectrum of these states compared to experiment. And again, the isospin mixing means that the physical states have been split apart, but the original states are basically on top of each other, and that's what the GFMC also says, although with some noticeable error bar. And in fact, there was an experiment being done in Mumbai for the 4+ to 2+ transition, and they contacted us to see if we had any updated calculations, and we said, well, we're just starting to work on this. Why don't you let us do some calculations for you? And so here's the problem in this case. Again, that's a physically wide state you're coming from, so it's a much tougher, it's both a tougher experiment and a tough calculation. The energies are fairly stable. You can see the 4+ state is drifting lower. That's the really wide state. The 2+ state is moderately wide. The ground state, although in principle it's decaying to 2 alphas, it's already at the 2 alpha energy, so it doesn't have anywhere to go. But if you look at the radii as a function of propagation time, you see, again, the ground state stays very flat, but after a little time, both the 2+ and 4+ states start to take off. And you also see that in the quadrupole moments. And consequently, since the E2 operator is basically R squared, you see the E2 operators start to take off after a certain time. But again, we make the approximation that, okay, most of the improvement in the trial wave function by the GFMC propagation has been taken place by here. The energies are pretty flat. We'll just do the same thing for pulling off the radius and the E2 transition mixture sum, and we'll allow for the fact that there's some uncertainty as to where it's best to read off. And so we end up with, in this case, a B of E2 for this state that they're trying to measure, a little bit bigger than experiment, but the experimental interpretation of the experiment is not trivial, so this is not that hard a number in some respects.
Is this constrained or not? I mean, the calculation.
These calculations, there is a constraint, and the constraint's being released after some
Even
time.
here, I mean,
But this is what happens. So these things really are starting. These states really are starting to fall apart, even with the constraint.
Even with the constraint.
Even with the constraint, they're starting to fall apart. And then these are just the calculations of the M1 mixing between those isospin mixed states, impulse, meson exchange current contributions for the total things. But then you have to do this, as I say, the mixing to get the physical states from the isospin pure states. And when you're all done, here are what the strengths of the M1 changes are. And the first 2 states come out pretty good. The next 2 states, yeah, so-so. And again, actually, there's a sort of an arbitrary sign to what the wave functions are. And normally that doesn't matter because you're usually just taking squares of, a B of E2 or a B of M1 is a square of a matrix element. So the sign doesn't matter. But in this case, because you're adding things coherently, you have to keep track of the signs. And we can keep track of that by doing that isospin mixing calculation earlier and making sure that our mixing matrix elements have the correct sign. So we've done some of the other sorts of things we do. I'll try to speed up here and not take too long. There are a lot of reactions, a lot of studies have been done over the years in light ion reactions, moderately low energy, things like a DP reaction where you're dropping a neutron into a nucleus to look at excited states of the daughter, the final state, or look at properties of it. A lot of this was done in the 60s and 70s. It's had a rebirth with the advent over the last 10 years or so of rare isotope beams where you can produce beams of rare, things that are going to decay in a second or two, but you can produce them in the accelerator. So a lot of these things can be done in inverse kinematics. For example, again, lithium-8 is about a second half-life, but and 9-lithium is even shorter. But you can, instead of doing a DP reaction, you can do 8-lithium, make an 8-lithium beam, scattered off deuterium, pick up a neutron, go to 9-lithium, and you can start learning things about the excited states in these and properties, make spin assignments and stuff. So a lot of the analysis of this is still done in a traditional distorted Wayne-Born approximation, but what we can do is provide nuclear structure input by calculating a different kind of off-diagonal matrix element. Basically, a body on one side, a minus one body. There's another particle that's just completely uncorrelated with the others on the other side. And the norm of this thing is basically what's called the spectroscopic factor. In a sense, it's an absolute prediction for what for the differential cross-section should be. And this has been, we've provided these to a number of experiments. And I just wanted to show it here again to emphasize this is a different kind of off-diagonal matrix element that we want to evaluate. The A body on one side, A minus one on the other side. And, but I won't go into any more detail on this. To say that the variational isn't too bad in the short range behavior, but the variational energies are often not quite right for getting the asymptotics, for getting the separation energies right. When you do the GFMC, in fact, for some cases, for example, this is 7 lithium going to 6 helium plus proton, so not taking a proton out of 7 lithium. It should have an asymptotic Whittaker function shape like that. The variational was up here, but the GFMC has corrected that, mostly by getting the thresholds right. And it hasn't changed the interior structure very much. So we not only can get these spectroscopic factors and wave functions to use as input to the distorted wave-Born approximation calculations, but we can also read off, in some cases, the asymptotic normalizations, which have dominate certain features of low-energy astrophysical reactions. The final thing I was just going to mention, these are somewhat several years ago now, but the one case we've done in scattering for GFMC, a number of you guys did these sorts of calculations earlier. I think you and Mal did helium-5 neutron alpha scattering at some point. Maybe it was in variational. I think it was in variational calculation. Variational calculations. The idea is basically the same as what you did. You're going to put 5 particles in a box, a spherical box of a fairly long radius, fairly big size. And you could, for example, think, okay, well, I'll just find the distance of, here's the alpha and here's the neutron. When it hits the edge of the box, there's some node in the wave function, the scattering wave function, there's going to be some node in the wave function. A more general thing is to just say, okay, at this boundary, we'll put a logarithmic derivative and keep the distance fixed. And then as we change that logarithmic derivative, repeat the calculation and see what energy we get. The combination of the boundary condition and the energy can be interpreted as, can be converted to a phase shift, so you can map out the scattering. So here's an example again of, if you had treated this neutron alpha for some particular, if you pretended it was a bound state, the blue dots, you would have, again, from variational starting point, a rapid drop and then this drift. And, you know, it's hard to say that that's an energy for it. It's just drifting off. It's breaking up to separated alpha plus neutron. But if you impose this sort of log derivative boundary condition, this is one particular value, you can see, you get down and get a perfectly stable result. So I have an energy for that derivative, and I can make a phase shift. And this is work that Ken Nollett really pushed to completion, did all the work of the actual details of making it work in practice. Here are shown on the left as a function of center mass energy. There are different partial waves. The 3½ state is the lowest possible state. There are calculations here with just 2-body force, which you can barely see, 2 plus older 3-body force, and 2 plus a newer but not the most recent 3-body force. And compared to our matrix analysis of the data. So the black lines are basically the experimental data you're trying to fit. And there's a 3½ and a first 1/2 excited state, and there's also a half plus, from which you can pull off a scattering length.
How do you implement that logarithmic derivative?
I'm sorry?
In GFMC? How do you implement it in GFMC?
Basically, you don't let particles go beyond the boundary, although you do pick up image contributions from just across the boundary.
So you solve for the propagator next.
Yeah, you let the particles be anywhere, but when they get close to the boundary, one, you don't let them cross, but you will pick up some little contribution going beyond. And more than that, I'd have to go back and look at notes to remind myself. So in the case of the 1/2 plus, it turns out it doesn't matter whether the 2-body force is already very good and the 3-body force has no effect. In the 1/2 minus state, the 2-body is off a bit, but adding either of these 3-body forces seems to fix it. But it's only in the 3/2 minus that you really seem to need this newer, more complete 3-body force to really match the phase shifts. And then here are the partial wave cross sections, and you really do see the 3/2 minus structure, definite resonant structure. And if you then just try to fit that shape to pull off both a location and a width of the pole, you're very close to the experimental value. The problems with this calculation are that there are tricks that to get to higher energies. Basically, we didn't let multiple nodes come inside the boundary, so we sort of had an energy cutoff. We didn't want to have to deal with a case, at least initially, where you had something like this happening, and here's the boundary. We were afraid you might get trapped on one side for a long time.
Well, you have to treat it as an excited state, right?
Yeah, what you really should do, you should do a multiple. In fact, Joe has done some of that in further things. You do a multiple state calculation.
Hamiltonian has Coulomb, one of our terms, right?
Yeah.
So
Well, in this case, though, the neutron is uncharged. The last 5th particle is uncharged, so it's not affecting.
Well, you still have charges in your problem.
Yeah.
And it would seem like you would have longer length scales, but
We found this boundary had to be pretty far out, like 9 Fermis. The alpha is a pretty compact object. It only has a charge radius about 1.5. But to get to an asymptotic regime, we had to push that boundary out to 9, which was more than we expected in advance. And that's another reason why we sort of haven't pushed this to other cases. If you wanted to do alpha deuteron scattering, the deuteron's a very diffuse object, and we're worried that we'd have to go to a much larger boundary. And we just haven't had the manpower to try that yet. Actually, maybe the next best case would be alpha-alpha scattering, which would be, again, interesting for a number of application reasons. So at any rate, I made it through in almost the right amount of time. Various conclusions. We claim we're doing pretty good. We have a good 2- and 3-body Hamiltonian that gives RMS binding energies that are, again, pretty good for nuclear physics, up to A = 12. And we've predicted in some cases radii and otherwise reproduced known densities and moments pretty well. And we've demonstrated, at least in principle, that you can do low-energy nucleon-nucleon scattering. There's actually an approximate way that I haven't mentioned for getting both ANCs and WITs out that Ken Nollett developed, and really works very well for single-nucleon stuff, and we're trying to do it for alphas coming out. There are a lot of things we're working on. As Alessandro talked about, we're doing more excited states in carbon-12 and transitions and electromagnetic sum rules, and the important goal is to do neutrino carbon-12 scattering because of all the experiments that are being done, for example, mini-boon. There are many more states in 9, 10, 11 systems we'd like to look at. We want to do more electroweak transitions. There's an interesting problem. The carbon-10 beta decay to boron-10 is used as input to eventually the extraction of the VUD matrix element of the Kobayashi-Maskawa matrix. And there's an important, the difference between the boron-10 and carbon-10 wave functions, which is very small. These are both 0+ states. It's a 0+ to 0+ transition. Is very small, but to calculate that important correction there. And what we're finding, at least in preliminary calculations, like our isospin mixing, is that Coulomb was only about half the story, and all these other charge independence breaking parts of the Hamiltonian basically double the size of that correction. Various other applications. Again, to go to something larger than 12, well, maybe we actually could at this point do, in terms of computer time, we could be doing 13, maybe 14, certainly by the next generation machine. Memory is something of an issue for us. To do oxygen in this manner is something like 1,000 times more expensive than carbon. So we're not going to be doing that real soon. A possible alternative is to do a cluster GFMC, or we actually did a cluster VMC back in the early 90s for oxygen.
What is that?
So basically the idea was you have a full 16-body wave function, anti-symmetrized, but just central correlations. And you sample that. And then within that, you look at all possible subclusters of 2 or 3 or 4 bodies. And within those subclusters, do the full operator structure of the wave function. And then you can do a linked cluster expansion to figure out what, see the convergences, the number of clusters of these subclusters are being evaluated. And that wasn't so bad for oxygen. And we're talking about trying to reinvigorate that program, because there are various applications. Those wave functions already have an awful lot of structure in them, and even the variational wave functions would be useful for some applications. Unfortunately, we had a postdoc, worked with Steve for 2 years to try and turn it into a GFMC cluster calculation, and it just never worked. The errors were never under control, and it sort of got abandoned. And that was about that time is when we went to doing straight GFMC for 6 and 7 body nuclei and push that program instead. Another possibility that we've talked with Stefano and Kevin briefly and other people is the possibility of doing a hybrid GFMC auxiliary field. The complaint I would have for auxiliary field is that the starting wave function has no tensor correlations in it, but in nuclear systems, tensor correlations are very, very important. Our problem, but the big advantage is that you sample that 2 to the 8 spin vector instead of evaluating the whole vector. What you could do is keep the whole spin vector but sample the isospin component, and that would save a factor of 100 over carbon-12 right now. So you could jump several nuclei in terms, you could put that into the spin part. That's something we really should try to pursue, and that would be obviously a big collaboration with lots of other people in this room and not in this room. Okay, I'll finish by showing this is an even more recent, although you can't tell from the date. What you can tell from is that the 2+ and 0+ state, second 0+ states have been added to this figure, and we've dropped off the 2-body just to make it a little bit less crowded.
More recent. Doesn't this evolve in imaginary time?
It does both. It evolves in complex time. Thank you. There'll be lots of time for discussion this afternoon.
Any more questions?
These M1 and E2 transitions, they are usually mixed. In an experiment, sometimes they are mixed.
Sometimes they're mixed, and we can calculate both components. We haven't tried to do, sometimes they measure, I guess, phase factors, basically. And we haven't tried to do that in any cases yet. But we should try to do that. In this case, these are only E2s. And the ones up there could be both E2 and M1, but the M1s tend to dominate. When they're both possible, M1s tend to dominate.
Well, it's a simple question. I just wonder about the